In this video, we're going to look at a couple of patterns associated with collection classes. This material is from Chapter 9 of the book, Head First Design Patterns. The iterator pattern provides a way to access the elements of an aggregate object sequentially without exposing its underlying representation. An aggregate object is a collection, like a list, a set, a map, or a queue. This description says that the iterator pattern allows you to iterate through the elements of a collection sequentially without requiring that the client who uses the iterator know what type of collection is being iterated over. Typically, the client will know this information, but that's not because the iterator itself is revealing it. Here's some types of aggregate objects. Now, you don't have to pause the video for this, though if you want to, you can. This is just a fun exercise. I'll give you 10 seconds to scan these images and see how many different kinds of collections you can recognize. 10 seconds starting now. Okay, in the top left-hand corner, we have an array. Underneath that, we have a set. Next to those collections, we have a list. Next to the list, we have a stack. Remember that a stack is last in, first out data structure. And next to the stack, we have a queue. A queue is a first in, first out data structure. So if someone's standing in line for, say, some tickets, the first person who gets in the line is the first person to get the tickets. In the bottom row, from left to right, we have a map. Next to the map is a tree, and next to the tree is a graph. Not all of these data structures have equivalents in the Java library. In particular, there is a priority queue in Java, but there's not a simple queue. There are implementations that use trees, like those for sorted sets and sorted maps, but there's no tree interface. And there's no general interface for graphs. This is a class diagram for the iterator pattern. The collection has a method that creates an iterator, and the iterator itself has a method called hasNext, which checks if there are still more elements in the collection to be iterated over. And it has a method called next, which returns a handle to the next element to be iterated over. Finally, it may have a method called remove, which removes the element currently being iterated over from the collection. You should be careful about using the remove method because it modifies the underlying collection. Most of the time, iterators are used to get information from a collection, like when you're printing out the collection or checking if one collection is equal to another. In general, you should avoid modifying the underlying collection if at all possible, as it tends to complicate reasoning, and in some cases, it can make the iterator behave in an unpredictable manner. Here's a question regarding this pattern. Why do we need a concrete iterator in this pattern? In other words, why not allow the concrete collection to simply implement the methods hasNext, next, and remove? Or maybe we can do it this way. Or maybe doing things this way is preferable. Please pause the video and try to figure out whether this is a good strategy or not. Not only that, but see if you can justify your answer. Ready? The answer is that we certainly don't need it. There's nothing stopping us from implementing hasNext, next, and remove in the concrete collection class. In fact, Java's iterators fully support this. For a collection to be iterable in Java, meaning that you can use the enhanced for loop with that collection, some people call the enhanced for loop a for each loop. For a collection to be iterable in Java, it can either implement an inner concrete iterator class, as shown here, or it can implement the hasNext, next, and remove methods in the class itself. So we certainly can eliminate the concrete iterator. But there's another question: should we eliminate the concrete iterator? And the answer, if you want to observe good design practices, is no, we should not eliminate the concrete iterator. The reason for this is that if the concrete collection class, the concrete aggregate here, implements both the collection interface and the iterator interface, then it's both a collection and an iterator. And this violates a fundamental design principle that says a class should be cohesive, which means that it should do one and only one thing. Either be a collection or be an iterator, but don't be both. Put another way, this principle says a class should have only one reason to change. And this is sometimes called the single responsibility principle. This principle gets back to the idea that our software systems will need to change. And the more we can separate areas of concern, the less chance we have of a change in one area of concern breaking something in another area of concern. A class has high cohesion when it's designed around a set of related functions. Every responsibility of a class is an area of potential change. More than one responsibility means more than one area of change. More than one area of change means that when we have to change something in one area, we run a greater risk of breaking something in another area. Let's move on to another pattern that is often associated with collections, the composite pattern. Recall that we said that Java does not have a tree interface in its collection framework. The composite pattern is sometimes used when a tree-like structure is desired. In addition to composing objects into tree structures, it also allows you to treat groups of objects the same way that individual objects are treated. Let's look at an example that many people might be familiar with, and that's the example of grouping graphical objects in a program with some kind of drawing capability. Let's say like PowerPoint. If I wanted to draw an American flag in PowerPoint, I wouldn't draw 50 stars and 13 stripes and move things around the screen individually. For the stripes, I might draw like one red stripe and then copy it 7 times. Once I get their spacing correct, I would then group the stripes so that I can move them around the screen as if they were a single graphical object. The stars would have even more groupings. For example, after drawing one star, I might copy it 5 times, group the 5 stars, duplicate it, add a star to the new group, and then I have a row of 6 stars, and I would place that row of 6 stars and the original row of 5 stars in proper arrangement, then group that and duplicate it 3 more times, and so on. The grouping allows me to move groups of objects around the screen as if they were a single object. Here's an example of the groups I might end up with in the drawing of an American flag. Notice the tree-like structure that's present here, and recall that for each grouping, it behaves like a single object with regard to moving it around the screen. this is exactly what the composite pattern allows you to do. Here's a class diagram for the composite pattern. This composite pattern is for an example that's similar to the PowerPoint one just described. An abstract graphic class has a draw method. The draw method is implemented by all subclasses. There are two kinds of subclasses: a composite class, picture, and various leaf classes. The leaf classes are line, rectangle, and text. All implement draw in their own way. The picture class has a list of graphic objects, and that's why it has add and remove methods. Since graphic objects can be leaf objects, or they can also be composite objects, that list of graphics inside of a picture objects could contain leaf objects like line, rectangle, and text, or it could contain other picture objects, or a mixture of both. Okay, the picture class implements draw by iterating through its children and calling the draw method on all of them. Before we leave the composite pattern, we should point out what some people think is a serious problem with the composite pattern. We just talked about the single responsibility principle. Well, the composite pattern violates this principle. It gives the composites the responsibility of maintaining objects in a tree-like structure, and it also gives them the responsibility of behaving like one of the objects they contain. This means that you should use caution when using this pattern and make sure you weigh all the benefits and drawbacks of this design with regard to your particular case. But then that's probably good advice when using any design pattern. And that's it for the iterator and composite patterns. We'll talk more about patterns in the next video.